Today's lesson, we're going to begin looking at the mathematics of chemical formulas. Up to this point, we've only written chemical formulas and discussed bonding. Today we begin the remainder of the course in chemistry, which will be entirely mathematical, and we'll look at relationships in chemical formulas and later in chemical equations. Our first quantity that we want to develop in terms of the mathematics is the concept of formula mass. And as the definition says here, a formula mass of any molecule, formula unit, or ion is the sum of all the atomic masses of the atoms represented in a formula for that substance. So we can use that definition to find the chemical formula for sulfuric acid and then determine its formula mass. Formula masses are in atomic mass units. Okay, so we want to find the formula mass for each of the following. This is the first one, sulfuric acid. Sulfuric acid is H2SO4. And what we have in this formula is two hydrogens. We have one sulfur, and we have four oxygens. So we have to think about what do we have when we say two hydrogens, 2 what of hydrogen? And that actually would be 2 atoms of hydrogen. 1 atom of sulfur and 4 atoms of oxygen. In order to get the mass of the entire compound, we have to sum the masses of all atoms. So what we would do is find, for hydrogen for instance, we would find the total mass in AMUs of 2 atoms of hydrogen. And we can say that every 1 atom of hydrogen has a mass of approximately 1.01 AMUs. This comes from the periodic table. We can say that every 1 atom of sulfur has a mass of 32.1 AMUs. And then do the same for oxygen. For every 1 atom of oxygen, we have 16 grams of oxygen. AMUs of oxygen. So we have 2 times 1.01 is 2.02 AMUs. We have 1 atom of sulfur at 32.1 AMUs per atom. So that's 32.1 AMU. And then we have 4 atoms of oxygen, with each oxygen atom having a mass of 16. So that's 16 times 4 is 64 AMUs. If we add all this together, we would have 98.12 AMU. And if we're only going to, if we're looking at sig figs, we would go to this location for the sig figs, and we would say that this is probably best written as 98.1 AMUs. Okay, so rather simple. All we do is find the mass of each element present in the compound and then add everything together. Let's try again with calcium nitrate. We've got calcium nitrate is CaNO3 2. So we have 1 atom of calcium. We have 2 times 1, or 2 atoms of nitrogen, and we have 2 times 3 would be 6 atoms of oxygen. So we have every 1 atom of calcium is 40.1 AMU. every 1 atom of nitrogen is 14.0 AMU. And again, every 1 atom of oxygen is 16 AMU. I'm taking all these masses to 1 sig fig. So we have 1 times 40, 40.1 AMUs. 2 times 14 would be 28 AMUs. And 6 times 16 would be 96 AMUs. We then sum this together. 40.1 plus 28 plus 96. It comes to 164. All of our, we're adding these together, so we look at how many decimal places to the right of the decimal. 164.1 AMU. So that is formula mass. The molar mass is the mass of exactly 1 mole, or 6.02 times 10 to the 23rd particles. This is Avogadro's number of a compound. So when we say particles, we're dealing with molecules, we're dealing with formula units, and we'll differentiate between those again in a bit. The subscripts in a formula, such as in H2O, for instance, represent, if we're talking about moles, if we say, well, let's look at it this way. If we look at 1 molecule of water, then we have 2 atoms of hydrogen and 1 atom of oxygen. But if we have 1 mole of water, then we have 2 moles of hydrogen and 1 mole of oxygen. So our subscripts, instead of representing individual atoms, can actually represent moles of atoms instead. And that's normally the way that we do it. Numerically, we can say that the formula mass and the molar mass are numerically equivalent to one another. The difference, just like in AMUs and moles back when we dealt with individual atoms, the difference is just the unit that you put after it. So 1 molecule of H2O has mass of 18.0 AMUs. 1 mole of H2O has mass of 18 grams. So we have 18 and 18, but our unit changes from AMUs to grams if we're dealing with molecules and moles. The unit, I'm writing grams here, but technically speaking, this is grams per mole, and this would be AMUs per molecule. But this portion is very often understood to be true, and we just write the mass unit, either AMUs or grams. But the formal unit for the molar mass is the grams per mole of compound. Molar mass, just as it could be in atomic masses, molar mass can be used as a conversion factor. And you should be able to convert between moles, mass, and number of particles, back and forth in any direction. So that's what our problem solving is going to look at for the rest of this video, is giving examples of each of these problem types. So let's calculate the molar mass of, let's start with barium nitrate. So we have, I'm going to start over here, BaNO3, 2. So in this, from a molar mass standpoint, we have 1 mole of barium, we have 2 moles of nitrogen, and we have 2 times 3 is 6 moles of oxygen. Notice that the pattern, the process is basically the same as it was before when we were finding formula masses. We then need a conversion factor to get us to to grams. So we can say that for every 1 mole of barium, we have 137 grams. The 137 comes from the periodic table. We have 2 moles of nitrogen, and for every 1 mole of nitrogen, we have 14 grams. And for oxygen, for every 1 mole of oxygen, we have 16 grams. So we have 1 times 137, 137 grams. We have 2 moles of nitrogen times 14 grams is 28 grams. And then we have 6 moles of oxygen times 16 for every 1 mole is going to be 96 grams of oxygen. This would be grams of nitrogen, and this would be grams of barium. Add this together. We have 137 plus 28 plus 96. And that gives a total of, add all those together, 261 grams per mole BaNO3 2. And let's do the same thing for aluminum sulfide. Aluminum sulfide is Al2S3. So here, according to the formula, we have a subscript of 2. That means we have 2 moles aluminum. And we have 3 for a subscript for sulfur, so that means 3 moles of sulfur. We need the mass for 1 mole of each of these, so we can do the multiplication. 1 mole of aluminum, 27 grams. 1 mole of sulfur, 32.1 grams. So this is going to be 2 times 27, that would be 54 grams, and this would be 3 times 32, would be 96.3 grams. And we add those together, 54 plus 96.3, so it would be 150.3 grams per mole of Al2S3. So the process is identical to finding the formula mass. The difference is that instead of finding the mass of one atom in AMUs per atom, we're finding the mass in grams of 1 mole of the element. Both of those numbers are the same and come directly off of the periodic table. When I say the same, that means they're the same number, not necessarily the same quantity. Now, we can use molar mass as a conversion factor to solve problems. That's what we're going to be doing here. So in this problem, we want to know what is the mass in grams of 2.50 moles of oxygen gas. Okay, so we have given to us 2.50 moles. Oxygen gas is O2. And we want to know what is the mass, and I should just write that as the grams of O2. Okay. So to get from mole to mass, we're going to have to multiply by the mass of O2 and a number of moles of O2. We want to cancel moles of O2. Now, when you look at the unit setup, grams per mole, this is a molar mass. That would be the conversion factor. In a conversion factor, mole is always going to have a value of 1. So we need to know the mass of 1 mole of O2, and that's going to be 16 times 2, or let's do it this way. In O2, we've got 2 moles of oxygen and there's 16 grams in every 1 mole, so that's going to be 32 grams per mole of O2. So we've got 2.5 times 32. It comes to 80 grams of oxygen. These should look very familiar to you. They're very, very similar. Exactly the same problems actually as what we did with atomic masses. We're just including masses for groups of atoms now. Okay, let's do another. Erase a little bit here. Alright, so we have the pain reliever, ibuprofen, and ibuprofen has a formula of C13H18O2, and it's a non-prescription pain reliever. We want to know how many moles there are in 500 milligrams of the drug. So very often you may find that you have an ibuprofen capsule 500 milligrams size, and we want to know how many moles of ibuprofen are there. Okay, so first thing that we're going to want to do is, well, there's 2 different things that we have to do. One of those would be we need to find the molar mass of C13H18O2. So we have 13 moles of carbon. We have 18 moles of hydrogen, and we have 2 moles of oxygen. So we have, for every 1 mole of carbon, we have 12 grams. For every 1 mole of hydrogen, we have 1.01 grams. And for every 1 mole of oxygen, we have 16 grams. So this is going to be 156 grams. This is 18.18. And this is 32. So our molar mass equals 156 grams plus 18.18 grams plus 32 grams. 156 plus 18.18 plus 32. That adds to give 206.18. All right, our next step in this is number of grams per mole of ibuprofen. The next step would be that we want to know how many grams we have in this capsule. So we have 500 milligrams. We're going to convert this to grams. Thousand milligrams in a gram, so this is going to be 0.500 grams. So you come up here and change ink color. And okay, so now we have given to us 0.500 grams. We'll let IBU stand for ibuprofen. And we want to know how many moles. we know from our molar mass here that in every 1 mole of ibuprofen we have 206.18 grams. So that gives us 0.5 divided by 206.18, and that equals 0.00242 moles of ibuprofen. That would be our final answer. All right, next problem. How many moles of compound are in each of the following? This is the first of them. We have 6.60 grams ammonium sulfate. Ammonium sulfate, NH4, 2, SO4. And we want to know how many moles. We're going to cancel grams. So we need to know the number of grams in 1 mole of NH4,2SO4. So that means we need a molar mass. So we need to add that up. So we will have, for every 1 mole of this compound, we have 2 moles of nitrogen. We have 2 times 4 is 8 moles of hydrogen. We have 1 mole of sulfur. And we have 4 moles oxygen. So we do our factor label. 1 mole of nitrogen, 14 grams. For every 1 mole of hydrogen, we have 1.01 grams. That's 8.08 grams. For every 1 mole of sulfur, 32.1 grams. And that's 32.1 grams. And then 4 moles of oxygen. For every 1 mole of oxygen, there are 16 grams. So that's going to be 64 grams. We need to add those together. We have 28 plus 8.08 plus 32.1 plus 64. That adds to 132.18 grams. So that's what we would put here. Every 1 mole of compound, 132.18 grams. We then divide 6.60 divided by 132.18, and that gives 0.0499 moles of compound. Okay, let's try another. We have 4,500 grams of calcium hydroxide, and we want to know how many moles. 4,500 grams calcium hydroxide, and we want to know the number of moles. Okay, so we have to find the molar mass of calcium hydroxide. We've got in our formula 1 mole calcium. We've got 2 moles of oxygen. And we've got 2 moles of hydrogen. So we have for calcium, every 1 mole is 40.1 grams. For oxygen, every 1 mole is 16 grams. And for hydrogen, every 1 mole is 1.01 grams. This gives a total of 40.1 grams, 32 grams, 2.02 grams. This is going to come to a total of 74.12 grams per mole. So then all we have to do is divide 4,500 by 74.12, and that gives us 60.71 grams of calcium hydroxide. Okay, our next problem, we're looking for a number of molecules. So we have 125 grams of sucrose, and we've got the formula for sucrose here. So we start with our 125 grams, C12H22O11, and we want to know the number of molecules. And we can connect that with molecules over grams. That would cancel grams here and here and give us molecules. Okay. Number of molecules is always going to be the same. We can add up a mass for a certain number of molecules directly from the periodic table. That is Avogadro's number of molecules. To get that, we have to add up the mass of C12H22O11 to get that mass. So that means we've got 12 moles of carbon, 22 moles of hydrogen, and 11 moles of oxygen. Every 1 mole of carbon is 12 grams. That's 144 grams. Got 22 moles of hydrogen, and every 1 mole of hydrogen is 1.01 grams. (22.22). And that would be grams. And then 11 moles of oxygen, with every 1 mole of oxygen carrying 16 grams mass. So 11 times 16, 176. So we get a total of 144 plus 22.22 plus 176. That adds up to a total of 342.22 grams. So then we have, just simply to do the multiplication and division, 125 multiplied by Avogadro's number and divided by 342.22, and that gives a number of molecules equal to 2.19. Actually, let's make that 2.20 times 10 to the 23rd power of molecules. Next problem. What is the mass in grams of 6.25 moles of copper 2 nitrate? Okay, so we want to know a mass. We want to cancel moles. We want to go for grams. Anytime we've got grams, we have to go to the periodic table and add. So we've got 1 mole copper according to the formula. We've got 2 moles of nitrogen. And we've got 2 times 3 or 6 moles of oxygen. 1 mole of copper is 63.5. Get a total of 63.5. 2 moles of nitrogen. That's 14.0 grams. And we've got 6 moles of oxygen. It's 16 grams. So that's 2 times 14 is 28 grams of nitrogen. And we've got 6 times 16 is 96. So our sum total is going to be 63.5 plus 28 plus 96. It gives a total of 187.5 grams per mole of copper 2 nitrate. So 187.5 grams. So then we multiply 6.25 times 187.5 to give 1,171.72 actually grams. From a sig fig standpoint, 1,170 is good. 3 sig figs. And that concludes the problem solving. This will be followed by a set of problems for you to attempt on your own during class time.